Today we're going to talk about building a multi-cloud Kubernetes storage environment for the very popular GitLab CI/CD suite. A little bit about MayaData first. MayaData is the company behind OpenEBS and sells the OpenEBS enterprise platform. OpenEBS Enterprise includes OpenEBS itself, OpenEBS Director, and the Litmus chaos testing suite. For our agenda today, we're going to go straight into a demonstration of a multi-cloud setup of GitLab on a test cluster that I put together. And we'll cover a little bit of theory about how you can design a multi-cloud or a resilient data infrastructure for GitLab, and different types of use cases that you might explore if you're tasked with putting this together. And towards the end of the webinar, we'll update you on the latest news from OpenEBS, and then we'll open things up for Q&A. So I would invite everybody to ask your questions in the Q&A section of the webinar interface, and that way we'll be able to read out the questions at the end of the webinar and get everybody's questions answered. With that, what I'd like to demonstrate for you today is an application GitLab, and in particular, we're focused on the Gitly component of GitLab. Now, GitLab is a source code repository as well as a CI/CD framework, and source code repositories are probably the most critical piece of information that a software development team needs to have backed up and needs to have access to. Everything else can be built out of that. And so our goal for this is to put together some resiliency around the Gitly component of GitLab. And the rest of the components we'll deploy, but we won't drill down into those. Where we're deploying is primarily in Packet. Packet.com has a bare metal cloud, and we're able to use some bare metal systems and some cloud systems from them to build a Kubernetes cluster. And then we added a couple of nodes on another cloud provider, DigitalOcean, and they happen to have a region in the same metro area as Packet, and so this cloud, or this cluster, spans two clouds in the New York metro area. As far as the topology goes, each node that we have storage on has a single SSD that's part of a CStore pool, and CStore is one of the storage engines that OpenEBS provides. We have two storage nodes in each cloud, and the way we've set up our CStore storage class, we'll be keeping 3 replicas. So 2 of them will be in one of the clouds, and 1 of the replicas will be in the other cloud. That's about it for infrastructure. Now, GitLab itself, I'll touch on a little bit. It's probably familiar to a lot of the attendees of this webinar, but it does have a free community edition with a working Helm chart. The Helm chart has some caveats, and some of those caveats are related to providing resilient storage for the Gitly process. It's an amazing piece of code and suite of software that allows you to store repo data in this Gitly component. They recommend that you use dynamic persistent storage when you're deploying in Kubernetes. And because of the contents, it's clear that they need backups, and that availability is critical for your developers to be able to work. So we're going to be focusing on this component here with the big arrow in it. And another word about the physical setup. It's a single Kubernetes cluster with 3 masters and several worker nodes in Packet, as well as several storage nodes. Now the storage nodes have a lot of additional storage in Packet that I'm using for other purposes, but I've taken 2 of the SSDs on the packets on 2 of the Packet storage nodes to use for this stretched CStore storage pool. And the other 2 nodes are in DigitalOcean, and the data flow is going to come in through SSH, through the ingress, and into this Gitly process. And then Gitly will use iSCSI to talk to an iSCSI target that will push writes down into the storage on 3 of these 4 different nodes. And so you can see in this diagram, I have lines drawn to storage locations in node 1, node 3, and node 12. And that matches up to where the storage is on the cluster itself. And of course, this is persisted on, it's ultimately persisted on SSD storage. So it has. Let me take a quick tour through the storage that we have here. So I'll launch right into the demo, and I'll illustrate a little bit about the physical substrate. We'll take a look at the storage 1 system here. And you can see we have a lot of block devices in here. And we have one of them that's claimed from the DigitalOcean box, and one of them is claimed from this box, and one of them that's claimed on storage 03, that all make up this CStore pool. Importantly, the network latency has to be pretty low in order for this to work. And so one of the other things that I'll illustrate while I'm on the storage node is that, and this is one of the nodes in DigitalOcean. You can see that the latency is under 2 milliseconds, which is really pretty fast for inter data center communication. Let's take a look at storage 11, which is one of the, or rather storage 12, I believe it was on, which is one of the DigitalOcean boxes. And we can do an LSBLK here. And we can see our dev SDA that we're using in the CStore storage class. So that's the physical machines that we have. If we take a look at this storage pool claim and storage class, I'll point out a few things here. First of all, this is a combined YAML document with the storage pool claim and the storage class concatenated together. The storage pool claim is up here at the top, and it lists out these block devices. Now, the block devices are able to be viewed just using standard Kubernetes commands and using custom CRDs that we've added to Kubernetes when we installed OpenEBS. So if we do kubectl get bd -a, we can see a list of all of the block devices. And if we take a look at one of these block devices with our friend grep, we can see that this is in fact on storage 11. So if we SSH over to storage 11, plus PLK, there's our dev SDA. And if we describe this block device, we can see that, yes, its path is at SDA. So, so we've identified exactly where in the storage environment the data is sitting. If we take a look at this SPC code, YAML again, I'll point out that this storage class references that storage pool claim, and it specifies that there be 3 replicas for any volume that's created there. And so if we take a look at the volumes that we have created, the PVCs that we've created in the GitLab namespace, there you can see the GitLab PVC is 50 gigs, and it's sitting on CStore stretched. So at this point, what I wanted to show is that really that Gitly is a functioning storage system for committing software to. And so I have something checked out here that I can just take a peek and make sure this works. Well, first of all, we should get the services and confirm that GitLab.GitLab.nyc is indeed that address. So we have our GitLab ingress coming in here, where we're listening on port 22 for incoming SSH connections. And if I do git remote -v, we have git at gitlab.gitlab.bmath.nyc. So we should be able to do a git pull, and we should be able to vi readme, maybe add some white space. And push it up. So that's persisted in Packet and in DigitalOcean now. To have a further look, if we take a look in the CVRs, you can see the status of the CVRs, just of the volumes, by using this command. So if we do a kube control get PVC -n GitLab, and take a look at this volume, you can see that these are 3 healthy replicas, and you can see the actual location of the storage they're on, based on this portion of the name here. So if you needed to trace down one of these replicas to a specific machine, you can take a look at kube control get pod -n open EBS, and you can grep for this string. And if we get the pods with O wide, we'll see this is the copy that's on storage 11. So that ends the demonstration portion of the webinar. Things that I'd like to investigate further in using a setup like this include having an additional ingress in DigitalOcean. And that would require some investigation as to whether or not you could have multiple ingresses accessing the Gitly process at the same time. And I'm not sure of the answer to that question. But certainly you could set it up as an active passive arrangement that had the application stack sitting in 2 different clouds, or manually set up the application stack in the second cloud as needed in order to get access to the source code. Other things of interest include service mesh testing, since all the traffic between the storage nodes is going over the public internet. Security is an important consideration in a setup like this. You know, further, you know, testing with something along the lines of Litmus to inject chaos into the environment would definitely harden the deployment. So I've developed this webinar to be a little bit backwards, and I did the demo up front, but here is, you know, sort of the why of multi-cloud. You know, everybody's technical deployments are susceptible to outages of some sort. And some of those outages are localized, but some of those outages are network-wide. And it's not, you know, it's not the cloud provider's fault. Equipment fails. It's just a standard situation when you're running a complex piece of technology that you're going to have outages. And so how do you mitigate those outages, really? What are the questions that come up after one of these outages? One of those questions is, why are you hosting in just one cloud provider? And why are you backing up to just one cloud provider? And so if you're in a position to have to worry about availability, then solving the availability problem for clouds that go off the net becomes, you know, an interesting challenge. Now, stateful applications are really the challenge when it comes to cloud lock-in. Stateful applications are sort of an afterthought for Kubernetes in general, and a lot of work has gone into it recently to provide support for stateful applications and stateful sets and all that. You know, but for complex large data storage requirements, the cloud providers generally recommend that you use their dedicated cloud services to store your data. That shouldn't be surprising. But some organizations have a need to store their data across multiple clouds. And that the reasoning, the drivers for that could be anything from, you know, price competition between the clouds to, you know, the receiving of a credit on one of the cloud hosting providers for an open source project. You know, it could be just about anything that might move you from one cloud to another. And so developing a multi-cloud strategy up front is important. You know, the other thing that I would point out about stateful applications is that Kubernetes is eating the infrastructure world, and it's definitely winning, and there's definitely a lot of interest in running stateful applications under Kubernetes. And you know, we at MayaData think that OpenEBS is really the best architecture for doing that. So how do you develop this kind of a multi-cloud strategy? Well, you want to avoid single zone clusters, single data center clusters for any of your production deployments. You want to make sure you have production deployments that are in multiple regions. And a lot of times, by the time you've solved for multi-regionality, you've got multi-cloud functionality able to be implemented with very little additional effort. So multi-zonal clusters are a good first step. Multi-provider clusters give you additional protection against network events. Federated clusters are something that's of interest, but you know, sort of a technology that at least I don't have clear visibility into a standardized way of setting it up. But that would be another interesting venue for further exploration. And the components that we're solving for, again, are the following components in a GitLab deployment. Gitly is the repository data, and it has all of the source code, and needs backups, and it's both read and write intensive for large code bases. But GitLab has other components as well, including it has an artifact registry, and so if you need resilient access to your artifacts, you might explore multi-cloud deployments with MinIO, various failover scenarios for that. Postgres needs backups and has performance characteristics that are very different from an object store or a source code repository. And so that's another area for future exploration, is providing robust storage for the Postgres components, as well as for the Redis components, which at the moment are deployed on OpenEBS hostpath, a different storage engine. So the Kubernetes native persistent storage is another possible way to solve this. And the folks at GitLab recommend that you use dynamic storage provisioning when possible. But if you were setting this up on bare metal and maybe you didn't have OpenEBS, then you could use the native Kubernetes persistent storage. The advantage to using OpenEBS for your persistent storage is that you can do multi-region and multi-provider replication with some of the storage engines. You can easily migrate your storage across to different cloud providers using the backup functionality that you can get from either OpenEBS Director or Valero or other mechanisms, and you have more granularity of control with OpenEBS than what you get with Kubernetes native persistent storage. So it's also completely open source. You retain control over your data, and you can reduce your cloud spending, which might be largely spent on data storage. So hopefully that discussion was useful. I'd like to point out that with OpenEBS, we do monthly releases and Litmus as well. And so we do releases typically on the 15th of the month. And 1.6 came out on January 15th, including a lot of bug fixes and some optimizations for Jiva rebuilds. 1.7 will very likely come out on the 15th of February. And it has a lot of exciting stuff in it, including the new storage engine MayaStore. And MayaStore is a redesigned storage engine built entirely in Rust from the ground up for NVMe use cases. And so it'll have the features of CStore with the latency characteristics of local PV. So that's in alpha now, and we'll have preview of that in 1.7. Also, one that's been in preview for a little while and is now getting released is ZFS Local PV, so that you can use local PV to dynamically provision volumes on a ZFS pool that's on your host. And so that's a use case that we developed in concert with one of our customers, and it's exciting to see that release. And also CSI drivers for CStore and Jiva. The CSI drivers allow us to communicate with other storage frameworks, so we can do exciting things like automatically expand your C-store pools. So that's all coming soon. Um, and I guess we'll open up the floor to questions at this point. Again, if I would invite you to add your question, type your questions in the question interface in the chat, and I think if I'm not mistaken, Trevor is going to help me out with reading some questions. Well, let me see if I can find the question interface here. Well, so we do have a question. I'll read the question out, and again, feel free to submit questions either on this topic or any OpenEBS related questions. I'd be happy to field. Question from Olivier: do you recommend local PV for min.io component of GitLab? I think that depends entirely on your performance characteristics. The min.io component of GitLab gets used for artifact storage, and those are generally reproducible. But sometimes artifacts are big, and sometimes artifacts need to be preserved for forensic reasons. So, the way that I have mine set up is sitting on C-store, and min.io can support its own replication as well, and so those are two options. Now, for local PV with 4 replicas, you will have probably better throughput characteristics than what you'll get from C-store, and the disadvantage is that there's a little bit more complexity in the fact that min.io now has to maintain its own storage synchronization, and so I think that there's advantages and disadvantages to both ways, but thanks very much for highlighting the fact that that there's more than one approach to tackling GitLab storage. And similarly for the Postgres database, a lot of the metadata gets stored in that Postgres database, and so I have my Postgres database sitting on replicated storage. But depending on the user community you're trying to support, you might want to get more performance out of it than that. Yes. Certainly for Redis, the faster the storage, the better, and that cache gets rebuilt when it comes up, I suspect. I would have to double check with somebody at GitLab on that, but I didn't consider worrying about Redis data protection as much as I worried about the Gitly data protection. And I'll point out that it was that this was a fun project to try and bring together, and I think that it would be an interesting use case for especially open source projects that want to have a centralized location, but don't necessarily want to be associated with one or the other cloud providers. I mean, there's a lot of uses for something like this. So if there's no further questions, we'll be at KubeCon. So we're really hoping to see everybody at KubeCon, and we have a booth. It's SC48. I'm excited to be there, and I know that a lot of our team members are going to be there, and so come say hello. And with that, thank you very much, and I hope you have a fantastic rest of your day.